Hello, everybody. Yeah, that was not very impressive. Hi, everybody. Thank you. So we have some disappointing news. AWS and Amazon in general is amazing at scale. We deliver packages in under 2 hours. We have global coverage for the cloud, billions of IoT devices. The one thing we have not figured out how to scale yet, is James Gosling. So James is unfortunately not able to make it today. He is at reInvent, so if somebody really had some burning questions and they'd like to talk to him, come find me afterwards and I'll see if I can do a little circle so everyone who's got questions for James and is sitting here going, oh, how do I get out of here quickly so that I don't embarrass her, can do so, get their questions answered. Anyway, since nobody's crying, we're going to talk a little bit about AI and IoT, hence the very clever acronym AIoT. In particular, we're going to dive fairly quickly into a number of different topics and try to create that story of how all of the machines are coming together and where artificial intelligence fits in to get more information and deeper information on a number of the topics which we will cover as far as AI goes. There are some sessions up there. In particular, that leadership session, not a very exciting title, but that's where my boss is going to stand on stage and tell you about all of our services in 60 minutes with several customers and what's new and what's come out in the last year. So he talks even faster than I do and even has more energy. It's very impressive. But that's kind of the catch-all session. The Industrial Insights one has also got some really exciting news coming out. There'll be a snippet of it in the other one. And then the others are deep dives into how customers are doing really machine learning with machines, which we will get into a little bit here. So what are we going to talk about, Sarah? Talk about a couple of key areas. One, you'll notice the machines and not IoT. Just out of curiosity, how many people here work in something that they would consider IoT, Internet of Things? Oh, good. Some hands. I've been doing this like, 15 years. And it's really good to see people not go, I don't know what that acronym means. Internet of Things is devices that are connected to the internet and or each other and then connected to the internet. We're going to talk kind of broadly here about everything that kind of fits into that sensor world of IoT, robotics. Really, it's things that are collecting data from the physical world and translating that into our digital world, which allows us to do all of our wonderful analytics on it, which kind of gives us our control over it. So one of the reasons why this was the topic that we are talking about today is because Thanksgiving just happened. And sitting around the Thanksgiving table, the first thing my mother asks me, and then my aunt asks me to repeat it, why do you do this Internet of Things thing? Where is this going? Are robots going to take over? Will you have a job? Will I have a job? And it's a very interesting topic, which keeps us off politics, so yay. But it's true. I have one of the best jobs in the world because I spend a lot of time with AWS customers talking about what their machines are doing for them. And many of them have millions of machines that are collecting data, that are doing cool things. I get to learn what makes a fish finder tick. It's pretty cool, actually. And it turns out you can do things like crowdsource sonar from fleets of fish finders on trawlers, right? I happen to know that pig facial recognition is a thing because it turns out, I know, it turns out if you're going to figure out which pig to breed to which pig, you better know who they are. Plus, vaccinations, you want an automatic feeder to be able to identify the pig. So, with all of that data and all of those machines, this wave of digital transformation, which again, All those machines are there for one thing. They're collecting data. That data helps us make better decisions, transforming many different industries. I know a number of you in the audience already. There are lots of people here who can tell you much more about this than I can. The interesting bit to me, though, is still the trillions, because we get used to big numbers. And you can think trillions of machines. You can also think trillions of dollars in, US debt. Either one. 1 million, which seemed huge when I was a kid, in seconds is last week. 1 trillion is back in 33,000 BC. That's a very big difference. So when you talk about trillions of devices, trillions of sensors out there collecting data, that's like having just sort of it's like the Matrix, basically. You got perfect data about a number of problems. So what do we do when we got all that data? We got all the machines collecting the data. First of all, lots of data coming in, right? Data streaming constantly off of these devices. At some point, I would like to think it's somewhere in the millions of devices, but honestly, it's closer to 4. Human scale data acquisition gets outpaced. And so the machines have to monitor the machines. Not terribly surprising. But what do we mean by monitor? Anyone who's done network monitoring thinks of monitoring as green light, red light, yellow light, right? Is it up? Is it down? Where's my SNMP trap? A little bit different when you start talking about machines that are collaborating and coordinating, right? Now it's not just red, yellow, green. You're talking about complex events. So complex events are events that happen across multiple systems, and you got to pull all that information in. This data is coming in at different intervals. It doesn't have any context. You've got to understand, when across a production line, when things start to kind of slow down, is that planned? That means you need data from your mom, not my mom, your mom, manufacturing operating manager. It's an application. It was a joke. It's okay. You gotta have information maybe from your planning system, your ERP system. You've got to have, obviously, data from the machines, or else I wouldn't be talking about it. Maybe you also have people standing on that production line who can tell you that the tape on the box keeps going askew, and so it's slowing down because somebody's going in there and manipulating it. All of that information has to come into a single place where we start to analyze it or reason over it. Now, when you get a paper mill, 20,000 sensors, trees go in one side, toilet paper goes out the other side. Very important processes make sure that that's good, high-quality toilet paper. All of a sudden, your complex events are dealing with 20,000 sensors plus hundreds of applications. Now we're looking at the probability that an event has occurred. We're talking about machine learning making those decisions. Again, we'll talk more about machine learning. Decision verification, your machine takes a decision. Was it a good decision? Was it a bad decision? This is part of the monitoring process that happens when machines monitor machines. Policing gets even more exciting. Now you get 2 distributed systems, both with different optimizations that they're making about their world and what they want to accomplish. How do you make sure that they're playing by the global rules, right? Now we're talking about policy enforcement. So lucky for you, the minute you give your machine a credit card, guess who they can buy all these skills from? You'll notice a couple of empty hexagons up there. Come Wednesday, pay attention to press. There's a few of those that will get filled in while at reInvent. If anyone is shocked by the fact that we're launching things at reInvent, welcome to reInvent. It must be your first. One of the interesting trends that we're also seeing, so this is kind of a little Easter egg in here, we see, I'm gonna say 2-3 years ago, most of the monitoring was kind of bottoms up. You'd pay attention to all the data and you try to synthesize it with the context to interpret it. What we've seen in the last year is people kind of go, well, that didn't work. I don't have the data density I thought I did, or I don't want to interpret it, or it's really expensive to do it. I'm going to try the top-down approach. Literally top-down in this case, usually a camera. There we go. That enables them to basically grab that context and infer the context of what's happening, right? Conveyor belt is slowing down. Is the box askew? Is that what's happening? Camera can figure that out. That's not a sensor that's today on the conveyor belt. So you wouldn't know that if you were doing the bottoms-up approach. Machines learning. Just going to start out with just a bold statement. We teach them. That's important, especially when you're looking at bias. Lots of different types of learning. Some of them are strategic, some of them are tactical, some of them are done by groups of machines, some of them are done by individual sensors on machines, some of them are done all over the place. So there are lots of sessions, by the way, on how to optimize those, what they do, and where they fit into the IoT space. One of the most important pieces for IoT about machine learning is that it's actually really hard. Machine data is hard to do machine learning on. Social media data, easier to do machine learning on. Go figure. One of the reasons, machines are intermittently not connected, so they have missing data. Another, probably more important, look at that data coming off of that machine. Like literally, this is what a lot of industrial systems put out. The time the measurement was taken, the time that measurement hit a particular aggregation server, usually an OPC UA server, a value, 5, and the unique ID of the sensor that measured it. I don't know what 5 is. I don't know if it's good. Is it bad? Is it my dog's temperature? That would probably be bad. Is it the fermentation level, the tank level in a fermentation beer? Probably also bad. I think I'd like it to be higher than 5, but I don't know. Is it 5 out of 100 or 5 out of 2? Is it gallons per liter? You see my point. All of that needs to be added into the data in order to be able to get the reference and be able to create interpretable models, except in some of the really interesting cases, like anomaly detection, where with a little bit of voodoo black magic, you can do anomaly detection without knowing a lot about the underlying things. Now, you still need that context in order to interpret, but it gives you a sense. I also am skipping over another really important piece about machine learning, which is dimensionality of data. IoT data often has high dimensionality. So you guys can go to a machine learning lesson and figure out why that's a problem. It basically means lots of compute and very complex algorithms. So again, a machine with a credit card can come and do machine learning with AWS IoT Analytics. In the IoT Analytics space, what we've done in order to address that really junk data that we get out of machines is we've put the analysis right in the same tool set as your data preparation and provided a couple of activities that make it easier to prepare and clean and process IoT data. Why did we do that? Well, machine learning likes pretty data. IoT provides crap data. So we make our crap data look pretty. But every time you do that, you're actually removing certain techniques from your quiver. Quiver being an arrow. Anyway, maybe not the best of words. But basically, as you clean your data, you can do things like remove outliers, which might be really good for certain techniques, like a k-means, but not so good for certain neural networks, which use some of those outliers for information and for kind of reference structures. So depending on the technique you're choosing to analyze your data, that's how you have to prepare the data. Also in the middle, if you are going to use certain techniques, require certain data structures, we handle that under the covers. The point here is that IoT and machine data requires having tool sets that bring a couple of key components together. Otherwise, you end up with 7 different people having to make 7 different decisions across 7 different tools, and the chances of them all making the same optimization on how to run their analytics is unlikely. So we see lots of customers who, when they build it themselves, end up getting junk results, and they're really disappointed because they have petabytes of data sitting in a data lake someplace that they're really hoping is the new oil. Strategic and tactical. Sorry, I went quickly past that. Strategic learning. basically planning, these are things that tend to happen centrally. So I also get asked a lot, well, what's going to happen on the machine versus centrally? Mom asks it the way of, hey, so who's got it right? Is it the Borg or, the Matrix, or, are robots going to take over one at a time? Which is going to happen in the future? And I have the unfortunate answer of, well, turns out, actually, strategic learning does very well in a centralized environment because of data gravity, right? All of the data for your context tends to collect. Tactical learning, however, where you are learning like signal processing, where you might be looking at vibration to determine whether something needs to be replaced, that happens locally much better. And the reason for that is because of the latency of decision. So, just in case you think I left, Thanksgiving dinner with the entire family in tears, I didn't. There are things that machines don't do well. We already talked about bias. Turns out, if you try to build a machine learning model to identify the best technical talent out there, it tends to lean towards men. Not because men are better, but because they are more part of the data set. We don't have enough women, so that bias gets built into the data structure and into the models themselves. Positive reinforcement is another one. If you take a kid and you point to a cat, 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 you never tell them that the dog is not a cat. You just only point to cats. The child will form a mental model. This is very well proven out within the language space about what a cat is and what a cat isn't. If you only show a model cats, it's not able to identify. You need to be able to kind of prune those decisions. You basically need to show it what is not a cat as well in order to be able to train that. So we're still good at some things. Also, just a little side note, robots have not figured out how to get faster than humans at creating a box. Right? That seems like something a robot should be much better than we are at packaging a box. But nope, we're better at it. So, machines collaborating. Clearly, they don't collaborate well enough to make a better box than we do. Machines are also specialists. So they have certain functions that they know and they do well, which means we bring them together. It's one of the reasons why that data structure is so simple on that robotic arm. It means you can put that robotic arm in any number of production lines doing different things without having to restructure the data every time. You got to do that after the fact. So, as these machines get closer and closer and they collaborate better and better, we've moved from where we have kind of a single product zone, that's that hospital bed with kind of connected equipment around it, to an area where we've got equipment from multiple vendors that coordinate. That's where that additive value starts to kick in. As you move further up and to the left, up into the, left, okay, good. You start seeing where you got multiple systems with multiple data types, all coordinating to be able to understand what might be happening, say, in an accident. So maybe you've got road sensors, you've got car in car, you've got CCTV from a building nearby, you've got streetlights that are connected, you've got lots of information coming in to coordinate. That's where we start seeing that kind of ability to add ambient intelligence because of the different dimensions that we've got on that data. Turns out, though, the challenge of getting from 2019 to 2025, and by the way, these are my dates. There's no hashtag Gartner underneath. Those are dates from observationally dates. But the way that I think we get to 2025, it's not a technology problem, it's a business problem. That additive value is very hard to redistribute. So for instance, if you have a Alexa in your home, which has you know what? This is one of the first times I've said that in a conference room and not had the little blue, like I actually looked, uh-oh, what did I do? But if you've got an Alexa, there's a microphone in it. If you've got a security camera, you've got a camera. If you wanted to go out and figure out you just recently had a baby, You could create a baby monitor out of those two functions, right? Video, sound, we're good. But today, you'd have to go buy another solution from another vendor, even though you've got all the functions in your house. The reason is there isn't a good way to kind of redistribute that value of, yes, I want the baby monitor function. It's a fairly simple example. It gets much harder as you get into more of these ecosystem plays. So, talking about ecosystems, and because I've been talking straight for 20 minutes, so let's look at some cool stuff. We're going to bring up Bob to talk us through an example of some machine collaboration with this cool thing right here, which is a microgrid that Bob has built, focused on kind of power arbitrage. So how do you make the right decisions about when to buy, when to use, what to use from which sources? Bob?
Hello, my name is Bob Edmiston. I'm a user experience researcher on AWS IoT. I specialize in the analytics space here.
Do you need to log back in over there?
Oops, hold on.
Just so that you can see more than kind of, you know, what looks like a flower up here, the solar panel.
Okay, camera's back up. We can switch over to that. So, I've been interested in renewables for a while, but how, as an individual, to make use of that in the workplace was a bit of a mystery. Actually, are we done? Oh, there we go. Okay. So, I decided one day, after realizing that we could purchase power on off-peak time at half price, I decided to create a laboratory scale microgrid for my workplace. So today, I run my workstation all day long on energy that I bought last night at half price. So, well, that's fun. The idea of driving the amount that I pay for energy down even further is interesting to me. So I built this setup. So here, this is a 24-volt battery stack. So this is a 1 kilowatt hour battery stack. And this blue box in the bottom is an inverter. This takes the battery power and turns it into a clean 125 volts AC, 60 cycles. And there is a solar charge controller, which can take anything from 30 to 75 volts and convert it into electricity that can be used to charge the pack. There is an Arduino here, and this is a Ruggedduino by Rugged Circuits, so it's really difficult to break this thing. So this takes voltage and amperage measurements every 3 seconds and relays that over to this Raspberry Pi, which acts as an IoT gateway. So the Raspberry Pi takes measurements and sends voltage and amperage to the cloud every 3 seconds to IoT Core, and IoT Core uses a rules engine to send that to IoT Analytics, and also to a complex event processing system that we have in the cloud, which can keep track of the state of this stack. So it monitors how much energy is being used. It measures the state of charge of the pack. So it knows if the battery is charged, if it's discharged, if it's discharging, or if it's charging. And it can send messages back to the system to turn on or off the inverter, and also to switch between renewables and the grid. So in so doing, I'm able to have the system automatically be controlled by the system in the cloud that's monitoring it, checking its states, and making decisions of when to buy electricity and when not to. And in the future, I want to drive the costs down by having the system in the cloud become smarter and be able to do even better complex event processing by learning how much energy do I use on a typical day, by taking data feeds from weather. So if I know that I'm going to have plenty of solar, how little energy do I need to buy tonight to satisfy my energy demands for tomorrow? So my goal is to drive that cost of the energy that I purchase smaller and smaller and smaller. And you may know, Amazon has a lot of employees and a lot of machines that use power. So the imagination that goes into these algorithms can be used at scale. And I think that imagination is the biggest thing that we need in order to solve some of these big problems, and having a platform to where we can play with our imagination to come up with ideas of how can we drive these costs down? How can we make the best use of renewables? We're just at the beginning of this process, but I made this as a way to create a platform to where we could start exercising these imagination skills. So stay tuned for later in the conference where a currently yet to be unnamed complex event processing thing might be unveiled to where you can play with it too. Thanks.
Thanks, Bob. So one of the things that, well, first of all, having Bob on the team means that every once in a while we have engineer-powered stand-up. So yeah, display, bike, engineer has to get his or her stand-up update done while pedaling to keep the display going. You're seeing where I'm going with this. Fastest stand-ups in the industry and fittest engineers. But part of the autonomous side of figuring out, how to get these various pieces of equipment, right, to work together, to coordinate across systems, regardless of what the vendor is, regardless of what the piece is. You started hearing Bob talk a little bit about kind of that functional abstraction layer. Charging. Doesn't matter if it's solar power, if it's an engineer on a bike, if it's a GM talking, if it's, I built a battery once based on temperature gradients in the body, if it's powered by you, that is just a charging state. So that modularity and that functional abstraction is very important for machines to be able to collaborate and soon to be able to design some of those systems without us. So we can go back to the slide deck. We will, by the way, take questions if we get done quick enough, and if we don't, we can meet people out. If you want to talk to Bob or come take another look. That was my placeholder slide on the off chance that we couldn't get the video to work. So, machines making machines. What happens to us when machines can make machines? I get this one a lot when we talk about what's coming up next, which is additive manufacturing. If they can make for spare parts or they can make collaborators be able to get things done, why do they need us? And it turns out, guess what? If you're going to make things, guess who consumes a lot of things, right? People. So actually, machines are democratizing the manufacturing process in ways that are very interesting. So without further ado, David?
Hello, everybody. Yep, I think it's on. All right. Well, thank you very much for Sarah and everybody for inviting us. My name is David, and I'm the Chief Product Officer at Formlabs, which is a 3D printing company. Super quickly, because I'm new to this crowd, this is the first time I'm here. How many people heard about Formlabs? Yes, thank you very much. And how many people have worked with a 3D printer? Okay,
Ooh,
more than I
few
thought.
more.
Awesome. So, 1 second, let's figure this out.
Yeah, the big green one.
Green one, all right.
Yep.
The one that looks like a logo. All right, so what I want to talk a little bit about today is how we can help make anybody, anything, anywhere on demand. I like to think about this as the AWS of manufacturing. So let's just jump into it. There is this paper that I think most people have never heard of. It's a really interesting one. It's from 1989 or 90 by a guy called Paul Davis. And he observed the Industrial Revolution, electrification specifically, and asked the question that why did it take a couple of decades from the late 19th century when electrification came about, a couple of decades later in the mid-20th century when you were able to start to measure the utility increase and the efficiency increase from electrification. There's a guy called Robert Solow that basically said we see computers everywhere, but in the productivity statistics, which means that we see, and this is also in the 90s, that you see similarly how electrification had this delay in it, computation had the same kind of delay in it. We have had computation being distributed desktop machines arriving on many people's desks, but still you were not able to see a lot of the efficiency gains. So there's this inherent delay between kind of the democratization of a technology and the impact that you can measure on it. And we see the same thing in digital manufacturing. And I wanted to dive a little bit deeper into understanding how we should think about it, and specifically about digital transformation. All right, so does anybody know what this is? It's a loom, close enough. It's a line drive, which means it's basically a transmission device used 19th, 20th century, basically to drive all sorts of machines. It can be looms, it can be CNC machines later on, and lathes, etc. And this is one of the things that really revolutionized how we make things. It was often operated by a steam engine in the bottom of a large factory. And when electrification came around, people were like, okay, how do we take electrification, how do we take this amazing electric engines and plug it in? Well, they didn't have a better idea, so they took the steam engine in the basement and they just plugged an electric machine in it. And that gave some benefits. It was more reliable, and it definitely had some marginal energy savings, but it was pretty lame. It didn't really deliver any of the supposable energy efficiency gains that people have been thinking about. And it was not until the kind of early mid-20th century when people figured out that the way to actually use this in a more scalable fashion is to attach the electrical engine into every single line drive instead of shoving it underneath and trying to just like kind of electrify the factory by changing one thing. And that really kind of took off. This is how a factory might have looked like at the end of the 19th century. It kind of looks like a fortress. It has a huge amount of energy stored in it. It's violent, it's super dangerous. And this is how a factory looked like in the middle of the 20th century. It's super open. It allows a single level architecture where you don't need to stack transmission systems and powertrains and stuff like that. And this really went beyond the initial benefits. We were able to have much safer, brighter factories. Architecture really improved in ways that it was safer. You were able to scale the floor. If you needed more manufacturing power, you were able to just scale it and add more individual line drives wherever you wanted it. And it was super flexible. So, takeaway. Electrification didn't make a difference until the factories were rebuilt ground up. It's not enough to just plug in the new technology and then wait until, I'm from Hungary, we have an amazing saying, which is that waiting until the roasted pigeon flies into your mouth. You can't just wait around and just expect amazing things to happen. You need to work for it. So this is very similar to how 3D printing and digital manufacturing works. This is a very expensive 3D printer. It costs a couple $100,000. And it's a great machine, but if you need more, you need to invest another $300,000, and you're not able to kind of plug and play. What we do is we make, these are our machines called the Form 2s, and the amazing thing about them is that they're $3,500. And they perform at the same quality standards as some of these larger industrial machines. And if you want to kind of draw this to scale, then it looks like something like this. You're able to really scale in the same amount of investment much further. And when it comes to manufacturing, it's not just about that one technology. It's always a collaboration between different systems, whether it's additive manufacturing, with CNC machining, subtractive technologies, and all over. It's always a combination of different technologies. So it's really important to condense it into a system that then can collaborate with other stuff. So this is the Form Cell. It's our attempt of creating a unit that demonstrates how you can really use additive manufacturing in a scalable manufacturing process. It's fully automated. It has a robotic arm that tends every single machine. And after the print has been done, it kind of delivers final part. The reason why I wanted to show you this because I think when anybody here thinks about manufacturing, this is what they're thinking about. This could be one of the manufacturing floors from an Apple factory or even an Amazon factory where you're making consumer devices. They are good to make a lot of one thing. It uses usually injection molding, the super repeatable, amazing process that once you have a design logged in, you're able to super quickly put out a lot of units. But it's very restrictive. And when we think about digital transformation and the way that we are rethinking that product development in general, it misses the point of really using the entire company as an engine for innovation. So this is one of the ways that we think about it. It's a when you look at a company and the different parts of the company, traditionally it's really just engineering, product design, and manufacturing that is involved in creating the core new product. It misses out a lot of the inputs from sales, services, marketing, etc. The reason for that is that there is just simply not enough time taking all of the feedback and feeding it into the engineering team. Our customers a lot of times are able to benefit from a much more holistic way of working with a team because you have direct interaction and the iteration cycle is able to shorten down. So why does this matter? The reason is we're able to create new type of products with it. Additive manufacturing and digital manufacturing in general is allowing to go beyond just the traditional make a lot of one thing, and instead of is able to create one or a few of individual parts for everyone here. So what we call mass customization is really a custom product for everybody. So whether that's CPAP masks that perfectly match your geometry of your face, that creates a much more comfortable experience, custom shoes, or custom earbuds. These are all examples of a world where we're going to be probably much closer to the customer, manufacture a custom piece depending on what the customer needs. And we already started doing some of this. We are working with New Balance, for example, on a custom shoe. We're working on a custom material that is going to enable them to not just make custom geometry, but also allow you to respond to the profile of your foot. We just launched this project a couple of weeks ago. This is a project with Gillette. If you go to razormaker.com, today you can design, and they will deliver in a couple of weeks a custom designed handle for your blades. And one of the things that I'm most excited about is custom earbuds. I'm sure that everybody has had this problem where you're running or just going about and earbuds just keep on popping out of your ear. Especially Apple ones are terrible for me. So what here we're doing is we're working with manufacturers to scan and then adapt and make custom earbuds for anyone. And we're actually at the place where we can go from a scan to a final printed part in less than 1.5 hours. So you can imagine a world where you can go up to a mall, get your ear scanned, grab a cup of coffee or go for lunch, and then come back and pick up your custom earbuds, which is super exciting. So I want to leave with one idea, which is, I think, a unifying idea between AWS and the Formlabs kind of strategy. I really like AWS, and we're using it at Formlabs from basically day one. When you have just an idea and you start scaling it, all the way when you have potentially tens of millions of customers, hopefully, and everything in between. And we like to think about our platform the same way. We're really trying to create a platform that is kind of unifying the prototyping and idea creation all the way to production. Because that's, I think, the place where most of the benefits and most of the exciting ideas will come out of. So I'll pass that back. Sarah?
So if you want to come see, I think 6, right? You helped set up. Do we have 6 of the Form 2s working? Yes. All right. The Builders Fair, which is in Quad which is, I think, down a floor. Let's see. Yep. Level 1. We're on level 3 right now. So go down 2 flights of stairs. Middle of that first floor is the Builders Fair. And if you head towards the Legos, and oh, by the way, they also have foosball where like 10 people can play at a time, so it's definitely, go check it out. But what I'm here to plug is the additive manufacturing demo that we've done, where the teams have worked together using IoT analytics to be able to analyze the print quality of dice that we're printing. Now, the print quality here is something where we are actually introducing some errors. So that doesn't mean that Formlabs has quality issues that we're just picking up on, and there are so many of them that we can do AR glasses. But we have populated the data from the print and the introduced error into the print, so that you can, when you wear the AR glasses, you can actually look at your dice that you get to take home with you. And it will give you the statistics on not just the data about the print quality itself. We've been building a model and a profile behind this, but it'll also figure out what likely you're likely to roll more often than not. So that, of course, is the issue with dice. These do not look anything like something you would take to the craps table. So, yep, I've already had somebody say, well, you know, the Gaming Commission, nope, they're big. They explicitly don't look like those. But it's a really cool demo, and you get a chance to kind of view a number of the services working together. So we have Amazon Polly acting as kind of the interaction agent. There's a digital assistant built into it, as well as Sumerian, which is the AR engine from AWS. And the team that's down there can walk you through very explicitly how we built the data pipelines from IoT analytics, what's being displayed where, and the architecture itself. So, thank you.